Jeff Spinks here with a brief update on the work that we're doing to try and understand the potential of heat engines that are powered by artificial muscle materials. We started by looking at Dr. Johnson's Clean Heat Engine, which is a heat engine powered by shape memory alloy and develops continuous rotation as shown here. It does so by cycling the shape memory alloy between hot water and cold water baths. Now, there are many different types of heat engines that have been developed over the years, and we were interested in understanding how the design of the engine affects its output. So we built these three types of heat engines and used the same shape memory alloy material and the same operating conditions to compare their outputs. The first engine used two pulleys that was synchronized by a belt drive. The engine started rotating by immersing the bottom part of the pulleys in hot water to cause the shape memory alloy to contract. We measured the engine output by lifting a series of weights. In this case, the maximum power generated by the engine was 3.6 milliwatts. The next engine used 5 shape memory alloy springs to connect two wheels. Each wheel had its own axle and used a bevel gear to connect to a single output shaft. Again, we lifted a series of weights and the maximum power generated by this engine was 20 milliwatts. The third engine used 24 shape memory alloy springs to connect two wheels. Each wheel was mounted on its own axle and the axles were offset by a small distance. This engine rotated very quickly and generated a maximum power output of 111 milliwatts. So the three engines generated quite different amounts of power, but of course they also used different amounts of shape memory alloy. When we accounted for the different masses of shape memory alloy used in each engine, we still found that the self-synchronized offset axle engine was the best, generating a maximum power of 34 watts per kilogram of shape memory alloy material, compared with 3 watts per kilogram with the gear synchronized tilt wheel engine and just 1.5 watts per kilogram with the belt synchronized two-pulley engine. One way to explain the differences between the engine performances is to apply a thermodynamic analysis. The work done per actuation cycle is defined by the area mapped out by the material's stress-strain curves. So the cycle begins by stretching the actuator from point A to B in the cold state, and then heating from B to C, followed by a relaxation in length as we go from C to D in the hot state. Finally, the cycle is completed by cooling the sample back from D to A. The area contained within these curves is the amount of work done per actuation cycle, and that's related to the power generated by the engine. So the differences in engine power can be related to the strain range imposed on the actuators by each engine design. The larger the strain range, the higher the power. Many more details on each of the engines is provided in the publication that's available at the address shown here. The publication is freely available. In our next video, we show how the analysis that we developed was used to design and develop a heat engine that used twisted and coiled polymer fibre actuators and showed the successful operation of that type of heat engine for the very first time. So, thank you for watching.